Hello, and welcome to this UCL Lunch Hour lecture on universes, multiverses, and simulations. I'm Andrea Sella. I'm a professor of chemistry here at UCL, and I'm going to be chairing today's lecture. So it's my real pleasure to introduce an old friend, Andrew Pontzen, whom I've known for many years. And I first met Andrew actually at the Cheltenham Science Festival a long time when he was playing the piano and literally singing the praises of the universe. And I must say, I was quite hooked. I've seen his talks many times before, and both he and my children, when they were younger and as they've grown older, have really loved his talks. Now, he's a professor of cosmology, and he's written a recent book called The Universe in a Box, which has just appeared in Italian as L'Universo in una scatola. And his research involves computer simulations to really understand the deeper parts of the cosmos. He's written for The Guardian, New Scientist, Sky at Night, and so on. He's appeared on all kinds of radio and television programs. And so he's really quite a high-profile figure from a physics and cosmology point of view. Now, before we begin, we're going to have time. Let me just tell you that we're going to have time for some questions at the end, and you can submit these at any point during the talk by using Slido. And you're going to need your web browser. If you scroll down into the lecture notes here on YouTube, you'll actually see the link. And there's either a link or you can use the event code with the hashtag multiverses. Anyway, without further ado, I'm going to hand over to Andrew. And yeah, let's hear about the multiverses.
Thank you. Thank you for that very generous introduction, Andrea. I am sharing those slides now, so hopefully you can see what I'm seeing on the screen. Shout if you can't. And thank you to everybody who's joining. Thank you for giving up your lunchtime. I hope I can tell you something interesting today. I'm going to talk to a large extent about how we go about doing computer simulations of our universe. Indeed, to some extent, of universes beyond our own, which is the multiverses in the title. It's quite a lot to fit into 40 minutes, but I will do my best to give you a taste for it. And I thought, a place to start is just to talk about the power of computers. I grew up in the computer age. And I grew up when having a ZX Spectrum was just the height of cool. I was so excited that we got this. It was a little sort of plasticky box that plugged into a television, and you could use it well, of course you could play games, but actually for me, it was much more exciting to program it to do what you wanted it to do. And one of the first program listings that I typed in out of a magazine was all to do with seeing how things orbited, how you could get stuff to orbit around a planet. And in some sense, what I'm doing my research today is a continuation of that. We have vastly more powerful computers now. So the way we can bring the universe into sharp focus and understand how all the different bits of the universe work together to produce a kind of vastly complicated universe and all of the phenomena that go inside it. I just find it incredibly exciting. It's one of the best jobs you can do as far as I'm concerned. But a few years ago, I kind of got interested in where did the idea of simulating the universe inside a computer actually come from? And that's what my recent book was partly all about. So alongside talking about some of the physics and so on, I'm going to try and give you a sense of that today as well. So where am I going to start? Well, I'm going to start with the universe as it actually is before we try to put it inside a computer. What do we know about the universe in reality? Well, if you go outside on a dark night here in London, you don't get to see very much of it. You see maybe a few planets, some of the very brightest stars, but not more than a handful of stars normally. But if you get away from London, if you go and see the night sky from a much darker area, and you allow your eyes to adjust, the richness of what's actually out there starts to become clearer. You know, your eyes adjust to see hundreds and then thousands of stars, and then after a while you also see a sort of faint band of light splitting the sky in two, and that's what we call the Milky Way. It's not sort of a amorphous strip of light. It's actually hundreds of billions of stars far beyond our own. And they're just so numerous that they kind of merge together into this band of light that we see across the sky. And I think to really appreciate just, you know, what that means, it's worth also mentioning that in recent years, we've been able to use telescopes to stare at some of these stars. And despite the fact they're so distant, we can actually measure the fact that they have planets orbiting around them. So they're not just sort of stars like giant nuclear furnaces all on their own. They're actually sort of ecosystems in their own right. They have planets orbiting around them. They're generating light and heat for those planets. And as far as we can tell, based on the statistics we have today, pretty much every star seems to be surrounded by some kind of planetary system. So in our galaxy, there are probably hundreds of billions of solar systems. And just to preempt one of the inevitable questions that always comes up, I mean, personally, I think the chances of finding life out there one day are probably pretty strong, just because there are so many of these systems out there. It would seem slightly unlikely that Earth would be so unique amongst those many, many systems. But in terms of what we do in trying to understand the universe as a whole and put that into computers, we're still here just seeing the beginning. You know, our own galaxy is in fact just the start of what's out there. And at the start of the 20th century, it began to be realized that there are many, many other galaxies beyond our own, and that those galaxies too contain hundreds of billions of stars. So this is our nearest neighbor large galaxy. It's called Andromeda. And if you want to see this for yourself, you certainly can. You need to know where to look. You need to be fully dark adjusted and ideally have a good pair of binoculars. But if you know what you're doing, you can find this on the night sky, and it just looks like a sort of smear of light. But it too is this collection of hundreds of billions of stars, very much like our own galaxy. And as I say, that's just the beginning. You know, the universe is absolutely packed with these things. In fact, what I'm showing you now is an image from the James Webb Space Telescope that launched a few years ago. And this image was released just last year and shows a tiny patch of the sky. It's around about, the full width of this is around about 1/10 of the diameter of the moon. So a very tiny bit of the night sky. And the James Webb Space Telescope was pointed at that one patch of sky and left to take a picture. And this is what came back. Now, everything that you see pretty much in this image, even the tiny, tiny dots, they are all galaxies far beyond our own. And all of that is just crammed into that tiny little patch of sky. So if you take this at face value and extrapolate up to the total number of galaxies in the universe, then you can put a lower limit on that at many hundreds of billions. So many hundreds of billions of galaxies, each containing their own hundreds of billions of stars, each of which may host planets. And that is the kind of scale of what we're looking at and the scale of what we're trying to recreate inside today's computers. But that still is the tip of the iceberg in some sense, because everything that you see directly, as far as we can tell, accounts for only 5% of the actual material that the universe is made out of. We have extremely good evidence along multiple lines of evidence that what you see is about 5% of what there really is. And there is another sort of 95% to the universe. And that 95% is made up of materials that are extremely unfamiliar, so unfamiliar that we've never really, or never at all, been able to experiment on them in a laboratory. They're two materials known as dark matter and dark energy. And those are going to have to be in our computer simulations if we want to have any chance of explaining what's going on in the universe. Because although we don't see them directly, they have a profound influence on what's going on. So the role of dark matter is that it essentially generates a great deal of gravity. It just carries a lot of mass around with it. The mass generates large gravitational pulls, and those gravitational pulls manipulate and drag around the material that we do see in the real universe. The other material is called dark energy, and that, again, is invisible. Just like dark matter, we can't see it directly, but it seems to have the effect of pushing material apart and making the fact that the universe is expanding. That's the first thing to say. The universe is getting larger, but it seems to be getting larger at an ever increasing rate. And dark energy is the material that is responsible for this. And these two things, they're just made up names in some sense. They are standing in for the fact that there must be additional materials to explain what we see. And I'm about to tell you what some of the evidence for that is. But don't take the names too seriously. They don't really mean very much, dark matter and dark energy. They're just standing in for what we hope one day will be a proper understanding where we can put these materials alongside the materials that we know and love, the atoms and molecules and photons and protons and neutrons and all of the things that we know and can experiment on in a laboratory. We hope to be able to fit dark matter and dark energy into that picture and really specify and pin down what they are. In fact, this is one of the main goals that we have when we're performing computer simulations. We can essentially do experiments where we imagine that the dark matter and dark energy is really made out of something specific. We put forward a theory for what these mysterious materials are actually made out of. Then we try programming a computer to follow through what the consequences of that would be for what we do see in the real universe. And to a large extent, this is driving forward this whole program of capturing the universe inside computers, is our quest to understand what these missing materials really are. Anyway, I've gone off on a bit of a tangent there. I want to kind of dial it back. We've seen, in short, what the universe is made out of and how vast it is and the kind of things that we're trying to capture. Let me just dial it back for a moment and talk about what the evidence for things like dark matter is. And you're looking actually at one of the strong pieces of evidence we have for the universe containing this additional stuff, dark matter. This is another image taken with the James Webb Space Telescope. Here you're seeing a bunch of galaxies, and again, in a distant part of the universe. But if you look at this, you'll immediately see that they're kind of bent into a particular shape. There's a sort of sense of a sort of circular pattern in the sky in this particular place. That is not because we believe the galaxies themselves have been bent by anything. In fact, we have very good evidence to show that the galaxies themselves are perfectly normal galaxies. They have perfectly normal shapes. What's going on here is that the light coming from distant parts of the universe is being bent. So it's coming from a normal galaxy, but on its way to Earth, it's being bent, and it's being bent just by gravity. So one of the things that Einstein's theory of relativity established is that as well as pulling material around, gravity can actually pull light around. And so as light makes its way through the universe towards our telescopes, it can get deflected. And we call this effect gravitational lensing. And what you can do with gravitational lensing is work backwards from the distortions in the images to an estimate of the strength of gravity that just generating those distortions, and then in turn to the amount of stuff, the amount of material you would need to generate that much gravity. And this is one of the key pieces of evidence that we have, that there must be extra stuff in the universe that we're not seeing directly, but that is contributing to generating this gravity, this very strong gravity that's required to distort the images of galaxies in this way. So that's one piece of evidence. But actually, the evidence starts to get really convincing when you throw simulations in there, because generally speaking, when you present a piece of evidence like that, people can counter it by saying, well, okay, but that's all based on assuming that we understand how gravity works. It's assuming that, although it's a very well-tested theory, we can't be 100% sure that Einstein's theory of relativity is correct. So maybe we're just miscalculating the effects of gravity. It's a slightly, it's possible to sort of undermine this evidence for dark matter in that way. But there's another piece of evidence for dark matter, which is based on simulations of physics, that's much harder to undermine. And that's based on contrasting the universe as it was when it was young with how the universe is today, and trying to fill in the gap between those two pictures using computer simulations. So in a sense, we're very lucky that light, although it travels very fast, it still travels at a finite speed. So that means if you look to large distances in the universe, the light simply has got to take a long time to reach you. Like anything, although it's going very fast, the further it has to travel, the longer it has to travel for to reach its destination. And we can use this to look back through time. We actually have special telescopes. This is an image from the Planck satellite that was an ESA mission that flew a few years ago, that really tuned into light from the very earliest age of our universe, a time when the universe was only about 400,000 years old, which sounds like a fairly substantial age, but in terms of a fraction of its current age, which is about 13.8 billion years, this really was a very, very young universe. And we can see directly what was going on, because the light, if you tune into the right kind of light, you find the light that's been traveling for all of that time. So you can see a picture there of what was seen by the Planck telescope. And you can immediately tell it doesn't look much like the universe today. I mean, I should say it's false color. The universe wasn't painted bright red and blue. In fact, all the light we're receiving is in the form of microwaves, which is a very long wavelength type of light. And then false color is used to highlight what are actually very, very tiny differences between one part of the early universe and another part of the early universe. So the red and blue patches here differ only by about 1 part in 100,000. It's that kind of level. They are very, very similar, actually. But the red bits have slightly more material in them, and the blue bits have slightly less material in them, just at the level of about 1 part in 100,000. Other than those small ripply type variations, the early universe was a very, very uniform place. It wasn't at all like the universe today, where we have, galaxies and stars and planets, and then vast spaces in between. The universe today is a place of huge contrasts. Some parts of it, if you go to the center of a star, it's millions of degrees. But if you go out into the furthest reaches of space, it's only 3 degrees above absolute zero. Whereas in the early universe, one part of it was very much like any other, and you have to kind of color it in this false color at the level of 1 part in 100,000 to see anything at all. So there's a fundamental question there, which is, how did the universe get from its early stages, a very, very smooth, uniform, boring place, to the remarkably rich, varied place that we find around us today? And the answer to that question has in large part been given to us by computer simulations, where we program computers with what we think are the most important physical laws, notably gravity, consistent with Einstein's theory of relativity. And we try to understand what happens if you start with the universe being very smooth, as we believe it did. What happens next? And I will show you simulations of this in a little while, but just to give you a sense of it, the most important thing that happens is if you have some region of the early universe which has just slightly more stuff in it than a neighboring region of the universe, there's a net gravitational force towards the region with more stuff. It's just got more stuff, therefore it generates a stronger gravitational pull, and it starts to suck up and sort of hoover up the material around it. And that process is a kind of runaway process. That what happens is that over time, those very slightly more dense regions become more and more and more and more dense, and gravity gets stronger and stronger, and the process runs away, and it builds the galaxies that we see. Now, the reason this is such good evidence for dark matter is that the process cannot happen without something like dark matter governing it. Because we find if we try to make this happen using just regular matter, then it doesn't work. Essentially, the pressure from the regular matter is too high, and the pressure tries to force the material back out again. There's insufficient gravity to actually pull everything together. And so what computer simulations of this process have been able to do is predict the process, predict how it works on the assumption that something like dark matter is there. And in fact, they've really done beautifully well at making those predictions overall, with some notable exceptions. But overall, they've been extremely predictive and extremely successful in accounting for this kind of huge contrast we see in the young universe and the old universe. Like I say, I'm going to show you that in just a moment. But let's now step back and, where did this idea of trying to simulate things come from? Well, like many things in computation, you can trace it back to the work of Charles Babbage and Ada Lovelace in the 19th century. Charles Babbage was inventing a machine that would be a sort of general purpose computer. You'd be able to instruct it to carry out any computation that you liked without physically changing the machine. You would just give it different coded instructions on punch cards. And unfortunately, the machine never got built, or at least not in full. And there are all sorts of reasons for that. But partly that Charles Babbage was an absolutely horrible person to work with by most accounts. He was extremely rude to the people around him. He sacked half his engineering team because he decided they weren't good enough. Then he resigned from his professorship in Cambridge because he decided Cambridge wasn't good enough. And then actually, I think he got cut off from his government funding because he became so critical of the government. He decided that the government wasn't good enough either, and his grants were cut, and the thing never got built. But its legacy lives on, largely thanks to the work of Ada Lovelace, who's a rather more sympathetic character, who had really thought about what this could be used for. And one of the things that she highlighted was that it was a way to turn physics from being a study of abstract and immutable truths, sort of with limited applications, applications just really limited by the handful of things that you could actually calculate by hand, which is relatively small. And it sort of promotes it from that abstract study into being something much more practical. Because if you're not limited by the human ability to calculate, if you have a machine that's able to do calculations of any type for you at more or less any speed, if you combine enough of them, then all of a sudden, all of these laws of physics that had been accruing become much more amenable to practical application. One of the first envisaged applications for this was actually weather forecasting. And weather forecasting has played a huge role throughout the history of simulations and has been deeply influential on the way that we think about the universe. But one of the things that it really highlights, and one of the reasons I talk about it a lot in my book, is that it's not enough actually just to have the physics and just to have a computer that can do all the calculations that the physics implies. You also need to know what we call the initial conditions. And in the case of weather, that means having really good, accurate measurements of what the Earth's atmosphere is up to today, if you want to be able to predict what it's going to be doing tomorrow. If you want to predict what a storm is going, whether there's going to be a storm here in London tomorrow, for example, then it's very, very useful to be able to track them coming across the Atlantic Ocean. And in fact, one of the first people who really followed this dream was Joseph Henry, who was, I think, the inaugural director of the Smithsonian Museum in Washington, D.C. And he had a weather map. One of his sort of prize exhibits was a weather map where every morning they would use the telegraph system to collate weather reports from across the US and put together a weather map of what the weather was like across the entire US that day. And this was a huge novelty at the time. People would come just to see this weather map, to kind of marvel at the idea you could know what the weather was like such long distances away. But Joseph Henry went a step further and started predicting the weather. He could look at it and, they were in Washington. He could see if there was a storm in Cincinnati, then he would be able to have a good guess that it was going to track and come over, and they would soon have a storm in Washington as well. So this idea of weather forecasting and the way it relies on the initial conditions was also something that sort of arose in the 19th century. And the first person who tried to put these ideas together, who tried to put the idea of just using brute force coupled to the laws of physics, and the relevant laws are things like the Navier-Stokes equations. These are equations that describe how fluids move around and how masses of air move around the Earth and so on. So you take those bits of sort of abstract equations of physics, you combine them with some initial conditions which represent the state of the weather today, and then you just do loads and loads and loads of calculations. And by brute force, you try to extrapolate what will the weather be like tomorrow. And the first person who attempted to do this was Lewis Fry Richardson. And he was quite a singular figure. I mean, what you're seeing here is just a tiny fraction of the calculations that he had to do. He had pages and pages and pages of these calculations. It looks like a giant spreadsheet, of course, long before there were any such things as spreadsheets. And he just did loads of manual calculations to try and figure out a weather forecast. Now, there was no way that he could do this fast enough for it to be a practical proposition. He was working with a weather forecast that would only kind of be predicting weeks and weeks and weeks of calculation would be taken to make a prediction for just a few hours of how the weather would unfold. And incredibly, he actually did this while he was serving on the front line of World War I. He was actually wounding people backwards, back from the front. So he was ferrying wounded soldiers back from the front, working for the Friends Ambulance Service. But in his sort of downtime, he was working away on these calculations and just wanted to prove a point, that this idea of calculating the weather in this very sort of brute force approach could, in principle, work. He wasn't really aware of the fact that computational technology was around the corner. In fact, when he got round to writing up this idea, his vision was for a giant purpose-built amphitheater where a bunch of mathematicians would sit each in their own room. There's a sort of zoom into this picture, you can see an individual calculator sitting at a desk. So he had this sort of vision of a giant amphitheater with lots of people working and passing each other their results, all sort of coordinated from a central pulpit where he would tell people what they ought to be doing. And somehow by working together, the idea was you could achieve the speed of calculation needed to make predictions for the weather ahead of time, rather than what he had been trying to do, which had just been, spend weeks calculating the equivalent of a few hours. And he proposed this in a book quite seriously, as far as I can tell. He was pretty serious about this vision. But in fact, it wouldn't be necessary, because within his lifetime, rather than anything like this coming along, digital computers actually came along. And the first digital computer to perform a weather forecast was the ENIAC, the famous computer that you might have heard about in connection with the end of World War II and the race to develop the H-bomb and so on. That computer was actually used to produce a numerical weather forecast using a lot of these same ideas. And that wasn't at all a coincidence. The military were deeply, deeply interested in weather forecasting. First of all, because just being able to forecast the weather is, of course, in itself deeply practical. But they actually had other ideas up their sleeve, that what they were hoping to do was to instigate a program of weather control, which was believed to be a sort of even greater threat in some sense to world stability. What was the idea that the USSR might be able to start influencing the weather. And if they could influence the weather, then essentially they would have something even more powerful than the H-bomb at their disposal. So the US started a kind of race to try and figure out how can we influence the weather. And as it turned out, that line of research got shut down fairly quickly, because it's extremely hard to influence the weather. Which is probably just as well. But that was what was at the back of the minds of the people who were developing these first numerical weather forecasts on the ENIAC. So we've taken a bit of a detour again into a very brief history of some of the numerical weather forecasting. So to take it back to cosmology, of course, there were people working parallel with this, having ideas about how can we get the idea of sort of reproducing cosmic phenomena inside computers, or even before computers were available. There were various attempts, like this one by Erich Holmberg. He used a bunch of light bulbs, actually. He had a laboratory at the Lund Observatory, and he darkened it. He blacked out all the light, used a bunch of light bulbs that he was using to stand in for stars. So they were supposed to be like a kind of an analog for galaxies, little stars that he dotted through his laboratory. And then he used the intensity of the light coming from the different stars as a way to kind of estimate the strength of the gravitational pull that they would produce. It turns out there's a very exact correspondence, in fact, between the intensity of light you receive from something, which drops off technically as 1 over r squared, and the strength of gravity that it generates, which also drops off as 1 over r squared. So he was able to use a bunch of light bulbs to kind of stand in for the stars in galaxies and try and figure out, using that, rather than have to calculate by hand what gravity would do to galaxies, he was able to do it sort of experimentally and figure out what happens if two galaxies collide together. And he came up with the answer that, well, essentially they fly towards each other and they throw out spiral arms into space. And this is a phenomenon that's now well recognized. It's something that happens in the real universe and that we see in our modern simulations a great deal. Here's an example from the real universe, sometimes known as the mice, of two galaxies that have kind of smashed together and thrown out a stream of material out into deep space. So Erich Holmberg was the first person, in a sense, to simulate that, but he did it with this sort of very analog approach rather than a digital computer. So if you fast forward a couple of decades, then you find the first digital simulation of galaxies. The first thing that starts to touch on what we do today was done by Beatrice Tinsley, who ended up at Yale University. And she actually changed basically everything that was thought to be known about cosmology at the time by asking a pretty straightforward question, which is, do galaxies shine with the same brightness over their entire life? And she came to the conclusion by putting together some quite simple bits of physics. with some best guesses, because it wasn't really possible, it still isn't possible, to capture all the bits of physics that matter. She had to write down some best guesses, for example, for the way that new stars can be formed out of clouds of gas, things like that. And she showed that it was just untenable. The idea that galaxies could somehow shine with a steady brightness over their entire lifetime was untenable. And that really mattered, because at the time, people had the idea that galaxies essentially are unchanging things, that they might vary slightly over time, but to a good approximation, they were thought to be essentially shining with the constant brightness over time. And a bunch of observations and the interpretation of observations had been based on that idea, including something as important as the fate of the entire universe was kind of bound up in this, because to map out the way that the universe is expanding today, you need to understand what you're looking at. You need to understand how bright intrinsically are all the galaxies that you're looking at. And people had just been making wrong assumptions about that. And by running some of the first ever simulations, Tinsley was able to show that there's no way that these things can shine with exactly the same brightness through their whole life. It just wouldn't work. And that basically changed the viewpoint on what the ultimate fate of the universe is, because it changed how we thought it was expanding, and therefore changed how we extrapolated that expansion into the future. It changed the picture from being a future where everything would ultimately stop expanding and collapse back down, and the universe would end in a few billion years. That was the sort of the old picture. It completely upended that and said, no, actually, if you interpret this more carefully, it looks more like the universe is going to carry on expanding forever. And that's still what we think is happening today. We still believe the universe will probably carry on expanding forever. So it was an early example of simulations really changing the way we thought about the universe. But I think one of the things that story teaches me when I unearthed it is just how important it is to realize that simulations don't have to be literal recreations of the universe. Tinsley had to make loads of very rough guesses at the way that galaxies behave. And it wasn't that she was trying to perfectly reproduce the way that galaxies behave. It was more that she was trying to understand the range of possibilities, what's plausible for how galaxies might change over time. And it was by doing that she was able to completely change cosmology. This is still the case today. We still have a bunch of things inside our simulations where we really don't quite know how to handle them. There's an example in weather, and in fact, in this specific case, climate change simulations. So this is Sikura Manabe, who won the Nobel Prize a few years ago for his early work on simulating climate change. And this is a diagram from one of his papers explaining how the simulations work. Part of them, yes, is about physics that's well understood and that is sort of uncontroversial. But another part of them is what we call subgrid. It's stuff that is happening that's sort of happening on scales that are just too small to capture inside a computer. So that might be in the case of weather, for example, small scale convection or the generation of small clouds, for example, basically impossible to capture on a computer. Even today, it's very challenging. So you have to make assumptions, reasonable assumptions about how those clouds might form. And, there's other things like the way that surface water drains away from the surface of the Earth once it's rained, for example. That's really important, but is extremely hard to capture in terms of just laws of physics. You have to make some reasonable assumptions and then test how sensitive your simulation is to varying those assumptions. So this is the kind of very important thing to realize about simulations. They are not literal recreations of our universe where we're just sort of revealing the truth about our universe. They're much more like imperfect experiments where we're capturing some useful insights, but we are not literally recreating anything. So just to recap, here's what you need to perform a good simulation. You need some initial conditions, which in the case of weather are given to us by present-day observations of what Earth's atmosphere is up to. You need some physics, which in the case of weather forecasting, it's about the way that gas moves. I mentioned the Navier-Stokes equations, things like that, and the way that light and radiation behaves. But you also need what we call a subgrid a model, which is all the stuff that our computer isn't powerful enough to get from physics, that we have to make some best guess assumptions about. And I don't think this will ever change particularly. Even though computer power is increasing very rapidly, there will always be processes that are just too small relative to the scale of the thing that we're simulating for us to be able to capture them using completely tried and tested, well-known laws of physics. For the case of the universe, this is much the same pattern. We have some extra physics that we care about, like gravitation and magnetic fields, but we have these kind of subgrid uncertainties. I mentioned the way that stars form is one of them. The way that black holes form and evolve is another one. Things like formation of dust in the universe, cosmic rays, the list could actually go on and on. And one of the really difficult things about simulation is making sure you're doing the best job that you possibly can of that subgrid level. But I wanted to mention also that we also have an issue with initial conditions for cosmology, because we have to be careful about what we assume about the early universe. We have some idea about what was going on in the early universe, thanks to things like the Planck satellite, which I showed you earlier on. But we also need to supplement that with some account of what was going on in the early universe. And I'm not going to have a huge amount of time to talk about it, but just to say that's given to us by a quantum mechanical idea known as inflation. And loosely, the idea is that in the very early universe, because the universe was so small, there was sort of quantum uncertainty. You can think of it as like ripples going through the universe. Because of Heisenberg's uncertainty principle, the universe couldn't have been completely uniform. It must have had some variations in density in there, rippling along. And that it's those variations in density which we later see in the cosmic microwave background, and which then get amplified to become the galaxies and so on that we know today. So if you put all of that together, then here is a simulation as they look today. You just saw the Big Bang, you saw the universe is expanding towards you. You'll see it starts out fairly smooth, but pretty quickly you start to get structures forming within the universe. You'll see that these structures are turning into like a kind of web-like structure. This is something known as the cosmic web. It's also been observed to exist. It's a kind of overarching organization for our universe as a whole on really vast scales. We're talking about hundreds of millions of light years here. What I'm showing you on the screen right now is actually dark matter. You wouldn't be able to see it if you actually lived inside this universe, but the dark matter is the thing that is generating this overarching structure for the universe as a whole. If you switch views and look at the visible universe, it looks like this instead. And now you can see there's just kind of traces of gas and also these bright specks where galaxies are forming. And if I fly through that, you can start to see that those individual specks resolve into billions and billions of stars. And if I restart time, because we're still fairly early on in the history of our universe here, then you can start to see these individual little galaxies build into larger and larger galaxies over time. It's through a process that we call hierarchical merging. And this makes very, very specific predictions. It's being driven by the dark matter in a simulation, and it makes very specific predictions for what we should find with telescopes. As I say, many of those, not all of them, but many of those have turned out to be accurate. So this is the state of the art, essentially. We're trying then to test different ideas for what dark matter and dark energy might be, and see what effect those have on the galaxies that form. And alongside that, of course, we're having to grapple with all of those subgrid questions that I posed earlier on. But I want to say one final thing, because I promised to talk about multiverses, so I have to get the multiverses in there. I said about the beginning of the universe is still quite difficult period of the universe's history to understand, and quantum effects back then were really important. And that means the amount of insight that we can get from our simulations on classical computers is really quite limited. It's difficult to simulate quantum processes on a classical computer. So most of our simulations are aimed specifically at understanding the later universe after the quantum effects have kind of frozen in. They've kind of frozen into just some waves, which we can then treat in a classical way. But what another sort of aspect of the universe that we'd like to understand is its very early history. And to do that, we're following a program of what we call quantum simulators. This is funded by the Quantum Technologies for Fundamental Physics grant that UKRI are supporting. And here, instead of using a classical computer, we use a quantum analog system. So this is actually something that you build in a lab. I don't build it in a lab because you shouldn't let me anywhere near a laboratory. It's a total catastrophe if you do. Our collaborators at Cambridge University are building this at the Cavendish Laboratory. This is a picture of what it looks like today. And what the experiment actually consists of is cooling things down to create what's called a Bose-Einstein condensate, where atoms start behaving in a kind of coherent way that's very similar to some of the physics that was going on in the early universe that I was talking about a moment ago. And in particular, one of the things that we're really interested in understanding is the potential for the early universe to not really just be a single universe. That because of the weirdness of quantum mechanics, one thing that can happen to that roiling mess in the early universe is that it can form little bubbles within it. So here is an animation of that happening. You can see a red bubble forming within a blue background. This is something known as a phase transition. The early universe may have gone through these phase transitions. And the red bubbles would essentially then be pocket universes of their own, isolated from each other. So our entire universe then would fit inside the red bubble that you see on screen, but it would have the implication that there could well be universes beyond our own. So we're trying to simulate this particular process in the lab. What you actually saw just then was a simulation of the simulation. So this is getting to crazy levels, but we actually tried to capture the physics that's going into the quantum experiment in the lab. We tried to capture some of that on standard computers to understand more about the experiment that we're doing. So what you just saw is not the experimental results. We're not quite there yet, but it's a sort of glimpse of what we're hoping the experimental results might look like, shedding light on the way these phase transitions happen and on the way they might give rise to not just one universe, but actually multiple universes. So I'm aware that I'm now very low on time, so I'm going to just skip through to my final slide, which is a bit of an advert that if this has whet your appetite, then I've written a lot about all of this stuff recently in this book. So please, if you're interested, then do get a copy and perhaps even review it on Amazon. But I think now would be a great time to stop and hand back to Andrea, who I think is going to share some questions.
Thank you very much, Andrew. That was absolutely fascinating. And what I found really particularly brilliant about it was linking together, scientific simulation in so many ways. One of the things just in chemistry that has really transformed chemistry from being one of those things where you're dealing with glassware and so on, the whole rise of computational chemistry and in the life sciences too, all of this computational biology. It's really brilliant to see the kind of breadth of stuff that is going on. So we have a number of questions, and for those of you who are online, what you might want to do is to actually vote up some of the questions, just so that we see what are the things which really intrigue you the most. But I'll take the question that's being voted up twice, and that is there are news articles that mention that images of the oldest galaxies captured by JWST, John Webb, John Webb, if I got
James
the right,
Webb. James Webb.
James Webb. Sorry, wrong saint. James Webb Space Telescope don't look as expected. And how do the simulations deal with these things? Now, perhaps if I could just link it to a second question that's there, is how do you simulate a universe in which you don't understand what dark energy and dark matter actually are and how they work?
Yeah, absolutely. So let's take the first thing first. So yes, absolutely. There's been a lot of very eye-catching press releases out there talking about, excuse me, talking about how the galaxies from, oh dear, the galaxies from James Webb are problematic. I take those with a very large grain of salt. So what is true is that there are some galaxies that have been found by James Webb, which is peering back a long way through time. So it's looking back to some of the earliest galaxies to form, long after the Planck cosmic microwave background that I showed you, but also long before the present day. And it is absolutely true that some of those are larger and brighter than we had anticipated. However, the problem is that the universe was a very different place back then. So it comes down to the subgrid that I was talking about. So if you're interested, for example, in how fast do stars form, then we have a very good guide to that by looking at the nearby universe. When we look at the nearby universe, we can see roughly how quickly stars are forming. And so that's a guide to these subgrid assumptions that we have to make to get the simulations to work at all. But if you base those subgrid assumptions on what you know about the present day universe, then you're not taking into account that the early universe was a very different place. And in particular, the chemistry, Andrea, you'll love this, the chemistry of the early universe was very different. And chemistry actually matters, believe it or not.
Of course it does.
because to form a star, you need to cool it down. You need to cool the gas down so that it can collapse and become really small before the nuclear fusion, that pressurizes it. Then nuclear fusion lights up and then it can become hot again. But there's this intermediate stage where it has to become very, very cool. And the way that happens really depends on the chemical makeup of the gas that you have, because the things that are doing the cooling are completely different depending on what chemical elements are there. So the most likely explanation for what's going on with James Webb is that we have over extrapolated about the way that cooling works in the very early universe. It's a slightly boring explanation, but it's by far, to my mind, the most plausible explanation. Of course, we don't know that for sure. I mean, it may be that once this has all been looked into in detail, we still go, actually, you know what, we still can't account for how those galaxies got to be so bright so quickly. But if I had to bet on it, I would bet that's going to be the answer, not some huge revelation in cosmology, as some of the news articles suggest.
Okay.
For dark matter and dark energy, we guess, and we have some pretty good guesses. Dark matter in particular, the fact that we haven't detected it yet here on Earth tells you that whatever it's made out of is very, very bad at bouncing off any regular materials, right? So it's what we call its cross section has got to be very, very small. And that, in an ironic way, that makes it actually quite easy to simulate, because it does very little other than pull things around through gravity. So it's quite sort of forgiving in a sense that you don't really need to know very much about it. You just need to assume there is some extra stuff out there. It pulls things around by gravity, but it doesn't make its presence felt through other forces. And that's sort of the core assumption that gets baked into these simulations.
Perfect. That's great. Thank you. The one question which I think is verging on the conspiracist, but it's great, is if we can upload the conditions of the universe into a computer to simulate and theorize about it, does that mean that it's conceivable that we are in fact inside a simulation, that the universe itself is some kind of simulation, and that we are within it?
Yeah, so I meant to talk about this, but I mistimed it. So it's great. And there's you know, a range of people have put forward that idea, ranging from perfectly serious philosophers like Nick Bostrom, for example, all the way through to perhaps slightly less serious people like Elon Musk, who has, quite seriously put forward the idea that, well, maybe we live inside a virtual reality. How would we know? And I'm very skeptical of this idea. I'm very cautious about this idea because I think there's two issues with it. The first issue is that it is such a wild extrapolation from where we are today. That our best virtual realities that we can create in cosmology have around 10 to the 14 bits in them. Bits is the unit of storage in a computer. It's about 10 to the 14. Whereas in reality, as far as we can tell, that the information in reality would need it would be a quantum computer, but it would need about 10 to the 124 bits. So there's really, there's a wild gap between what we're able to do right now and what we're talking about when we talk about could we be inside a simulation. Now, could that gap ever be bridged? Well, actually, no, the answer is no, because you can prove that you would need to use the entirety of all the material in the universe to build a computer capable of simulating the universe. So, it's not actually going to be possible ever to do that. Now you can layer ifs and buts on top of that, but I think at the heart of it, it is such a wild extrapolation that it's a mistake to take this seriously as though it's a scientific proposition. Really, it's not saying very much more than, you go back to, I don't know, Descartes or Plato, like shadows on the wall of the cave. Yes, there may be some layer of reality that's inaccessible to us, but that's not really in the remit of science. And I think it's a mistake to say that anything we're doing in science right now points in that direction.
So we only have about 2.5 minutes left. So let me just throw some quickies at you. And one is, how do you enthuse young people living in urban centers about astronomy with no nightscape due to light pollution? This is from someone who's in a dark valley in the South Pacific, which is brilliant. But coupled with that, what impact do you think the vast number of new satellites being put in orbit by people like you just mentioned him, Mr. Musk and Mr. Bezos and so on, will have for enthusiasm for astronomy and cosmology?
Well, I think
Quickly.
it's tricky. Is the first is the answer to the first part of the question. But there are schemes that take people from urban centers and take them out to see the beauty of the night sky, and that, of course, is an expensive and involved thing to do, and it's very hard to reach large numbers of people in that way. But I think ultimately that can have a profound impact on people. And short of that, of course, you can also go and talk to them and show them images, but it doesn't have quite the same impact. In terms of polluting the night sky with satellites and so on, I doubt it's going to have any negative effect on people's enthusiasm for astronomy, but it's certainly a huge headache for people who are trying to take professional observations of the night sky. It's incredibly difficult already to take a long exposure image of the night sky and not have one of these damn things come in front of your camera and make a complete mess of it. It's causing a lot of problems.
Thank you. Now, I was going to take two questions about simulation, but I think we're really, really close to time now. And so maybe what we should do is, first of all, to thank Andrew for such a great and thought-provoking presentation, which has covered such a wide range of areas. To thank all of you for attending, and just to point out that on Thursday, we've got a really important talk to mark International Women's Day. And that's asking the question or making the statement why we need to teach everyone about reproductive health. And this is a really big question in the current political climate. And so I hope that you will drop in on another one of these lunch hour lectures here from UCL. So thank you very much for coming. I've certainly learned a lot. And Andrew, thank you again. It's been a real pleasure. I'm just sorry that we haven't been able to have lunch together today, but we'll do that sometime soon. Goodbye, everyone. Take care. Thank you for coming along.